For another example of a hypothesis test, and this is probably a more common example, often we want to compare two different populations using samples from each population. It's a rare thing where we have an actual understanding of what a population mean and a population standard deviation are. So often what we're going to do is we're going to take a sample from process A and a sample from process B, and we're going to compare them. In order to do that, we need to use what's called a two-sample t-test. So let's run through an example of this. There are different types of reloading dies, and these reloading dies are used to reform cartridge cases from target rifles. And the die here that we see on the left is made by a company called Forster. Their dies tend to cost quite a bit more, and the internal structure of this die is significantly different. It's quite a bit different than that of a conventional die from a producer such as Lee, a well-known company that sells very low-cost dies. You can see that the difference between this single die from Forster, which is $73, and this die set, two die set from Lee, this includes another die that does something completely different, is only $20. So one might ask, is the average runout improved by using the Forster die instead of the Lee die? And when I say average runout, I'm talking about a case runout dimension that's well known among target shooters. Basically, when I reform that case, is it going to be very consistent in terms of geometry, or is it going to be less consistent? I want to know whether it's worth this extra cost. Is there an actual performance difference between these two designs? So I'm asking the basic question, is average runout improved by using the Forster die instead of the Lee die? But we need to translate that into kind of experiment speak. So the way that we can restructure this question is to say that we have a null hypothesis. The null hypothesis would say that there is no difference in average runout between parts produced with the Forster die and parts produced with the Lee die. The alternative hypothesis, the one that would kind of state the difference that we're looking for, is that the Forster die produces parts with less average runout than the Lee die. I want to know that the Forster die is consistently better, in other words, less runout. So that alternative hypothesis is going to affect the way we structure our experiment. So we can derive a few characteristics of the experiment that we're going to run by the way that we have structured it so far. First, we're comparing mean values from two small samples. Mean values means we're going to be using a t-test of some sort. Because the samples are small from both sources of information, in other words, I'm trying to compare a small sample from the Lee die to a small sample from the Forster die. I don't have the population information for either. As a result, I need to use a two-sample t-test because I'm going to be doing t distributions for each instead of the single-sample t-test like we do in another video. The alternative hypothesis, H1, states less than instead of simply unequal to. And what that means is I need to show that the Forster die is less than the Lee die in the runout that it produces. It's no good if the Forster die goes above. I want to show that it's going to one side only. That changes the nature of the lookup value that we get from our t-table and will thus change the result. So we're going to call that a single-tailed t-test because we're just going less than instead of unequal to. Also, there's no reason to think that the variances should be the same between that production from the Lee die and that production from the Forster die. The two dies work differently. As we said, the mechanisms are quite different, and the things that might introduce variation are probably going to differ as well. So as a result, we are not going to use a pooled variance. We're going to do a t-test assuming unequal variances. You can use a pooled variance if you assume that the variance will be the same from one to the next. In other words, if the sources of variation should not change, then you might use a pooled variance. But in this case, we're not going to do that. So, knowing that we need a two-sample t-test assuming unequal variances, then we can go to just about any statistics text and go get the equations for that. These equations look a little bit dizzying, but they're actually not that bad. It's just plug and chug. You just got to make sure and check your work. Remember, with a t-distribution, we have to define a number of degrees of freedom because that defines the overall spread of the probability distribution. In other words, we need to know effectively how many how many readings we've taken, but because we've taken possibly two different sizes or two different numbers of readings and my standard deviations vary, I need one new value to look up on my t-table. So I calculate that using this equation. Here, the standard deviation S is the sample standard deviation from each one, respectively, Forster and Lee, and N is the number of replicates. So if I made 7 or 8 cases with Lee and 10 cases with Forster, then I would put in 10 for the Forster number and 7 here for the Lee number. And so you just plug and chug, calculate your new value. One thing to note, new is always rounded down to the nearest integer. In other words, if you get 24.2, then that was 24. If you get 24.9, that was 24. New is the next lowest integer, in other words, counting number. And then we can calculate t with this equation here, which is the two-sample t-test equation, assuming unequal variances. And so each variance is taken into account along with its respective number of replicates. Here, the mean difference is switched because I want to see Forster less than Lee. And if I had some threshold, like if I wanted to know whether the Forster die produced at least 0.02 of an inch less runout than the Lee, that would be a slightly different question, and I would put that 0.002 right in here where I see a 0. In this case, we're just trying to show that the Forster produces less than Lee. We're not trying to specify by how much. So, this is real data. Between these two dies, the Forster die, I made 10 cases with it and got an average case runout of 2.225 or 2.25 thousandths of an inch, the standard deviation of 0.702 thousandths of an inch. And with the Lee die, I got an average runout of 4.81 thousandths with a standard deviation of 1.6 thousandths. And for reasons that I don't recall at the moment, I only got 8 replicates from that particular set. So, if we take these numbers and plug them into the equations from the previous slide, I get nu is 9 degrees of freedom. I go to my t-table, and I'm going to use that to determine my critical t-value. With my t calculation from the previous slide, I'm showing a t-value of 4.253 between the Forster and Lee. And so what I'm going to do is I'm going to go to a t-table, and here we see that we have a critical value of 1.833. We come over here, it's single-tailed, so at a 5% level of significance with 9 degrees of freedom, I see that my critical t-value is 1.833. So because my t-value of 4.253 is greater than that, we're saying that the difference between these two means is greater than the difference that we would need to show significance at the 5% level of significance. In fact, if we use an automatic calculator, you can even look it up on this table if you look at a more complete table, but any automatic calculator will give you what's called a p-value, or the minimum level of significance we would have to be willing to accept in order to show a difference. And in this case, my p-value is 0.001. What that means is that I have a very high level of significance, a very significant difference here. And so the Forster clearly does produce less runout than the Lee die, assuming that our experimental method was good. That's how you run a basic two-sample t-test.